JavaScript operates on a single execution thread, processing instructions strictly in sequence from top to bottom, one operation at a time. When a time-intensive operation enters this thread, like a network request taking 2 full seconds, the progression stops completely, waiting for data. A frozen execution thread means a frozen user interface. Browsers rely on this same thread to render pixels and register clicks. If the thread is waiting on data, the user is locked out of the application. The language requires a mechanism to process time-delayed operations while keeping the main thread moving forward. To understand how modern JavaScript handles this tension, we have to trace its evolution through 3 distinct patterns of handling non-blocking sequential data. Let's establish a baseline test environment. We have a function called dataGet that queries a database and imposes a strict 2-second delay before returning its result. This execution timeline shows what happens if we fire 3 distinct getData requests concurrently. The engine processes them in parallel in the background, and all 3 pieces of data arrive simultaneously at the 2-second mark. But concurrent fetching fails when systems have strict sequential dependencies, situations where step 2 mathematically cannot begin until the data from step 1 is validated. Consider a standard authentication flow. The system must query the database to verify a username exists. Only after that data is confirmed can the system execute a second query to check the password. Because the second request relies entirely on the outcome of the first, developers have to build control structures that explicitly force the code to wait before advancing. The earliest architectural solution for enforcing this order was the callback function. You pass a secondary function as an argument, instructing the engine to execute it only after the primary task completes. Looking at this code block, we instruct getData to fetch ID1, passing a nested function holding the command for ID2. To add a third sequential dependency, we place the request for ID3 entirely inside the callback of ID2. Instead of extracting data and returning control to the main thread, this structure forces the execution path to plunge deeper into its own internal logic. This creates deep chains of lexical scoping. Each nested layer retains access to the layer above it, entangling memory. The number of sequential dependencies determines the indentation depth, forming a geometric shape known as the Pyramid of Doom. As the application scales, the logic bloats horizontally, becoming dense and difficult to track. Error handling in this model requires redundant manual checks. If a network fails, developers must write unique error logic at every single level of indentation to catch it. This is a hard scaling limit. The logic breaks down because we are passing control inward to the function, rather than requiring the function to return a manageable result outward. To dismantle the pyramid, JavaScript needed a mechanism that returns control back to the main thread immediately, long before the requested data actually arrives. That structural fix arrived in the form of the promise object. A promise is a stateful proxy. It acts as an IOU representing the eventual outcome of an asynchronous task. This logic node shows its initial form, a neutral pending state. The backend operation executes independently. The promise object itself simply acts as a listener, waiting for that background task to declare an outcome. When the backend successfully returns data, the promise permanently locks into a fulfilled state, capturing and holding that specific data payload. If the operation aborts due to a network failure, the promise shifts to a rejected state and ejects an error code. The asynchronous function no longer dictates what the application does next. Its only responsibility is to update the state of this one object. To extract the data, the main thread attaches a .then handler. This mechanism listens for a fulfilled state and unpacks the payload. To manage failures, the thread attaches a .catch handler, creating a centralized location for intercepting a rejected state. By encapsulating future data as a tangible, stateful object, promises successfully separate the background execution from the main thread's handling logic. We can apply this new promise model directly to our 3-part sequential fetch. Look at this structure. GetData for ID1 returns a promise. Inside its .then handler, we explicitly request ID2, returning a new promise. Because it yields a new promise, we chain the next .then directly below it, maintaining a perfectly flat left margin. Compared to the old callback architecture, the deep nested logic physically collapses into a neat vertical stack. A single .catch handler appended at the very bottom of the chain will now securely intercept a rejection from any of the 3 preceding steps. While structurally sound, developers are still forced to wrap their application logic in .then functions rather than writing raw imperative instructions. Promises fixed the inversion of control, but the syntax itself still didn't read like natural top-to-bottom synchronous code. This brings us to async and await. These do not replace promises. They operate as strict syntactical sugar layered directly over them. Placing the await keyword in front of our getData promise executes the exact same functionality as the .then block under the hood. Mechanically, await forces an execution yield, pausing progress until the promise settles. On our execution timeline, the main thread doesn't freeze. It bypasses the paused function, yielding control to the event loop to manage other tasks while background data fetches. We fetch all 3 dependencies simply by declaring variables and writing await before each call, one after another. The .then callbacks are eliminated entirely, leaving asynchronous sequences that read exactly like linear synchronous code. To use this mechanic, the engine requires labeling the surrounding function with the async keyword. This acts as a mandatory flag, explicitly allowing execution yielding within that scope. Async and await bridge the gap. They provide non-blocking background execution packaged in the exact same readability as synchronous code. This introduces one final structural constraint. Because await requires an async function wrapper, it cannot be executed freely at the top level of a script. To run an asynchronous sequence autonomously on load, developers use an immediately invoked function expression, an IFE. You enclose an anonymous async function entirely within grouping parentheses and append an invoking pair of parentheses at the end. This creates an isolated lexical scope that the JavaScript engine defines and executes immediately, bypassing the top-level constraint. JavaScript overcame its single-threaded bottleneck by chaining callbacks, flattened the resulting logic structures using stateful promises, and optimized the developer experience by yielding execution via async and await.